Thank you. Thank you for the introduction. So I will talk about our work on behavior simulation for smart contract. This was a PLDI 2020 paper. So this is a joint work with Gabriela Ciocali at University of Texas San Antonio, and Michael Ami from at Amazon Web Services, and Konstantin Enya at Ecole Polytechnique. So smart contract, we can think of them as ordinary programs that execute blockchain transactions. In particular, a smart contract is constituted of fields to store the contract state and methods which execute transactions. We can differentiate between two types of methods: observers, which we use to query the state, and imitator, which we use to modify the state and transfer assets. Here we have an example of smart contract for token. So here we have two fields to store the token states, and we have an observer balance to you give it an owner address, and it will return to you like the balance of that address. And we have a imitator which transforms a given amount from one address to another. Generality and bugs and smart contract are critical because, like smart contract like tokens, they manage billions of dollars in digital assets, and also when they are deployed on the blockchain, they are immutable. We can distinguish between two types of verification that we can do to prevent bugs. First, byte level analysis, where we can specify certain vulnerability patterns and look for them. And there is also like high level verification at like high level programming language like Solidity, where we can analyze functional property and we can do modular verifications. In our work, we focus on the high level verifications. In particular, in high level verification, a verifier will expect to give a contract that is annotated with specialized specifications that are expressed over the contract field. For instance, here we have a first condition over the increment that the value will be the old value plus 1. And we have multiple verifiers like sausage verify, verisol, and verex, which will tell us whether the post condition is held or not. However, in reality, these specialized specifications, they are extracted from annotated contracts that don't have any annotation, and some generic specifications that characterize the sequences of invocation that are agnostic to the state representation, because you can imagine that this contract can be written in different programming languages, or the state can be represented differently. So here we can, like for increment, we can just say that when you do the get the first time, you return 0. When you do get after increment, you get 1, and extra. To the best of our knowledge, like extracting this specialized specification from this generic specification, they are not generic tools, and that can express this like specialized specification formally, which means that it will be very expensive in terms of human time and effort to do this. So our goal here is the automatic verification of this annotated contract via semantic comparison with annotated contracts. So here, this will allow to verify safety and hyper safety of the annotated contract, and to infer the specialized specification of this annotated contract by doing semantic comparison with the annotated ones. So this is our goal, and this is based on the observation that most of the smart contracts are variation of a small set of reference or canonical contracts like token, fungible and non-fungible, auctions, and escrow. So the idea here is to manually annotate a small set of reference contracts with formal specification and to verify them, and to automatically verify the larger sets and the much larger set of annotated contracts via semantic comparison with the reference contracts. So our semantic comparison corresponds to simulation relation. In particular, given an annotated contract, let's call it a source S, and an unannotated contract, let's call it target S. A simulation relation between the two contracts is a relationship between their states, such that it includes the pair of initial state of both contracts. And if we have two states that are related by the simulation, for each invocation on the source that leading to some other state S prime, there is an invocation of the same method in the state of the target that lead to some other state T prime, such that S prime and T prime are related by the simulation relation. So this gives us, like, if we extract the simulation relation for the unannotated contract, its specialized specification will be the conjunction of the specialized specification of the target contract with the simulation relation. So let's look at this simple example of the increments. So here we have the target contract where we have the specialized annotation of the post conditions. And we can see that the other source contract, it has a simulation relation where, like, we can say that x equal x prime divided by 2. So here, if we assume that those two post conditions are the specialized specification of the target contract, the post condition of the source contract will be the conjunction of the post condition of the source contract with the simulation relation. Now, how our work will be to synthesize this simulation relation. In particular, we are going to use data-driven learning, where we say we want to learn some candidate simulation relation that will separate between a set of positive examples, which are the set of pairs of state that are included in all simulation relation, and a set of negative examples that are the set of pairs of state that are excluded from all simulation relation. So let's say those two regions represent these two sets. We can know that we always learn from a finite set of examples. So assume that we learn, like, we're given like finite set of negative example and finite set of positive example. Then we learn some separator between those two sets. However, as we can observe here, not every separator between the two finite sets will be a good simulation relation, will be a valid simulation relation. Because this separator here, it includes some set of negative example. It excludes all finite set of that we use it to learn, but the general set of negative examples, some of them are included in the simulation relation, and some of set of positive example are excluded. So we need to verify that this candidate simulation relation is indeed a valid one by making sure that it includes all positive example, exclude all negative example, and it is inductive. So how we extract those positive examples? Here, the positive example is a pair of states that are reachable from initial state when invocation are executed in lock steps. So assume that we take the initial state as 0 and as T0. We take a lockstep execution of both contracts, and we continue the process until we get a sufficient set of positive examples. For negative example, are pair of state from which observationally different state can be reached with lockstep execution. Assume that we have two sets where we will execute the observer on their state, we get different observation. So any state S and T that with lockstep execution we can reach these two states, these are a negative example. Now, a counter example that there is no simulation relation, if with a positive example, we can reach observational different states. So this is a counter example. This is like when we do like the generation of positive and negative example. If we found something like this, we can stop there and say there is no simulation relation. So let's look here in this example of before, where we present it as a state machine. So first, like increment, like for the first source, increment by 2, the observer divide the x prime by 2, and for the other, we increment by 1 and we return x. So here, one positive example are the initial states. Then we take lockstep execution, we take another state, and we follow the same process. A negative example is if we take S0 and T1, we know that we can if we take lockstep execution from T1, we reach like T2 where x equals 2, where we observe x2. And from S0, we reach S1 where x prime equals 2, and we observe x prime divided by 2, which is 1. 1 is different than 2. So with lockstep execution, we reach observationally different states. And similarly for S1 T0. So here we generated a set of positive and negative examples. We use some data-driven learner to separate between these two sets. For this example, like taking x equal x prime divided by 2, we'll separate between these two sets of examples. Now, we want to verify what we learned. So here we build a contract that is the product of the two contracts. And the separator that we learned before is a valid simulation relation if it is an inductive invariant of the products. So the correctness of this statement is based on some deterministic assumption on the contract, which is valid since smart contracts are deterministic in nature. So let's take this two-state machine and do the synchronized product of the two. So here the synchronized product, this initial state is the product of this, is the synchronized product of the initial state. Then we do the increment. Here the increment of the synchronized product, call both of those increment. And we continue the same process. Then we use some modular verifier where we verify that the separator is an inductive invariant of these products. And in this case, it's valid, since like x equal x prime divided by 2 is indeed an invariant. For instance, if we want to implement this in real smart contracts, so here is how we build the product. So we have the two initial contracts, and here is like the product. So the increment of the product we'll call the increment of the two contracts, and the constructor we'll call the constructor of the two contracts, and the get and the read we read both contracts, and as post condition we make sure that they return the same values. Now we implemented this in a tool where we have Explorer to generate negative and positive examples by running the actual contract on private blockchain ganache. So it takes the annotated contract, the unannotated contract, transaction parameters. It generates negative and positive example. If there is no simulation relation, if it found counterexample, it return a simulation counterexample. We then use the negative and positive example in a learner that is an extension of the PI, which is a shortening for precondition inference engine, which was published at PIDA 2016, where we extended it with the new grammars and to adapt it to our case. Then we learn some separator between these two sets of negative and positive example, and we use a verifier where we build the product contract that is annotated as an invariant with the separator. And we use the sources verifier, which is a modular verification tool that is built above on Boogie to check whether the separator is indeed an inductive invariant or not. So we tested the tool using a set of 3 annotated contracts that represent different typical smart contract classes. So this is a set of reference contracts. Then we used 41 annotated contracts. Each one is associated, such that each one of those reference contracts is associated at least with 1 annotated contracts. And we use also 2 annotated multi-contracts that are associated with 3 different annotated contracts. So this is the experimental result. So I don't expect you to read. So like this, what the column there is like the skeleton of the simulation relation that we found. And here, like the verifier is what we verified or not. So to summarize, 41 out of the 43 cases we were able to handle. We were like for 3 out of the 41, we found simulation counterexamples. So that means the unannotated contract, they don't find the reference contract. So we found that those indeed correspond to some vulnerability in those contracts. For 3 out of the 38 remaining, we were not able to verify the simulation relation that we generated. This is because like some contract, they need some kind of loop invariant to help in discharging the pre and post conditions. For the 35 were we able to verify simulation relation. The simulation relation, something that is nice about them is they are mostly are conjunction of equalities. So they are like easy to learn from data. And most of the learning used only 100 positive and negative example. In the worst case, we used 450. So to conclude, I proposed an automated verification of annotated contract based on simulation synthesis. The existence of simulation implies the inheritance of the safety and hypersafety property of the annotated contracts. And the technique that we presented is complete modular the deductive verification, the learning from bounded example, and the simulation proofs. As a future work, we plan to eliminate the need for the transaction parameter by using inductive learning so that we can learn from the verifier count examples. If like we were not the simulation, like the separator is indeed not a valid simulation relation. Also, like we can automate the identification of the relationship between annotated contract for a given annotated contract, maybe using some machine learning classifier. And another also extension, maybe we can also use some loop mechanism to help the verifying the discharging the pre and post condition. Thank you.
All right, we have some time for questions. I guess we can't pass the microphone around for questions since that's the only one.
Yeah, they would have to come to the front, or we would have to repeat it.
Okay, well, you can ask and maybe you can repeat.
Okay, no problem.
Hi, great, so thanks.
No problem.
I was wondering, how do you differentiate between like a contract that is not conforming to the original like ERC20 token and one that might be kind of just changing it to be like maybe the token doesn't allow the owner to change. So like, how do you differentiate between something that's broken and something that's just changing the original?
So yeah, so that's indeed valid question. So for instance, for the three cases that we show that the question was about whether like when we find that
Testing. Yeah, it's connected to the room, but not to the.
Oh, now it works.
I know what happened. Okay.
Okay.
Keep going. Use
Okay.
this microphone.
okay, I didn't. Okay, so I need to be like this.
No, you're fine. The microphone, for whatever reason, was
Okay.
not active for a few seconds.
Okay, no problem. So indeed, like this is like for instance for this cases that were there is no simulation relation. We were not simulating the contract themselves. Like there was like bugs in those cases, but for other cases, let's say for smart contract that has let's say some kind of let's say mechanism or guard that has allowed to behave less than the reference contract. In this case, for instance, when we define the simulation relation, we say that if you have a transition in the source, you will have a transition in the target. So if you don't have that transition in the unannotated contract, you don't need to prove that there is one in the annotated. So like here, it's not a B simulation. So that is one way you can use it to only say that one of them simulates the other, but the other doesn't simulate. So here you can use like saying that I don't need B simulation. I know just one of them simulates the other. So this also will apply if you have multiple contracts, like say ownership with ERC20 with some kind of whitelisting. That's are in one contract. You can use this. And yeah, and also like one other problem that is important that was also published in PRI 20 by another paper is if you have negative, if we have counterexample in the verifier, where do we put that counterexample? In the set of negative example or the set of positive example? So that's also like something that we are looking at because like you just get a counterexample of simulation relation. Is your simulation relation weak or strong? If it is weak, that means you need some positive example to strengthen. If it is strong, that means you need some weak. negative example to weakness. So there, like, there was a paper about PLI 2020, but it was mainly about how you use data-driven negative and positive example to, in the counterexample loop, how to classify the counterexample. Is it going to the negative example set, or is it going to go to the positive example set? And we are looking if maybe in the simulation relation there can be something more that kind of, because that paper was about the general context of data-driven learning using the negative and positive example. Okay, another question.
More questions. So I had a curiosity about the learning part. So you're using, I guess you're using a learner that was proposed in prior work, but you modified it. Can you say a little bit about how you, like how it works and how you modified it?
So the learner is called Pi. It's really like nice work. That also like the paper that I mentioned was also like by a similar group from the author. So the idea there is to have some grammar, and from this grammar you are going to build expression, and the learner will going to go through this expression by complexity, and they going to go until it finds like expression that is going to separate between the set of negative and positive examples. In our case, we needed like to define new kind of grammars, because like before the grammar was specific to OCaml, like the tool was built like for OCaml and for recursive function, so we needed to adapt it for our purpose. And also something that we need before, like the tool was using concrete evaluation. You give it like the value of negative. When you evaluate the function over this, you give it the concrete value. For us, the evaluation happened on the blockchain. So when you want us to evaluate some candidate expression, we need to take it, the candidate expression, and run it on the blockchain. So we need like the evaluation part of that tool, we need to adapt it so it communicates with the private blockchain to evaluate expression. So here we do some kind of
Interesting.
like the evaluation. Before it was concrete, but here we send expression to the blockchain to evaluate it.
Yeah. Cool. Well, I guess as a follow-up, I was surprised at how effective your technique was able to be, getting so many examples verified. Do you have just because invariant inference is a critical part of the technique and it's known to be really hard?
Yeah.
I'm wondering what is it about this domain that made that you were able to take advantage of to be successful?
Like that. What like I mentioned like in the slide here is that something nice about simulation relations. There are many conjunction of equalities.
So there's a lot of data that's the
They
same.
like let's say this field equals that field in that other contract, and here the learner that will enumerate by the simplest to the more complex, and the equality usually go through them first.
Yeah.
So that's why like simulation relations are really like the sweet spot of this kind of invariance, and we were also like surprised by this and excited about it.
Yeah. Good. Another question.
Yeah.
Different question. I was wondering your use of SolC verify.
Yeah.
How do you find it in terms of its strength at proving what you wanted?
Okay, so like source verify. So like this work was done almost like 2 years ago. So for the last year, I'm something like the developer of source verify, because I know they are no longer working on source verify. So it's not maintained currently. But at that time, let's say if you like, because now also like smart contracts are very complex. So like at that time, like talking about a snapshot of 2020, at that time it was really good. But now smart contract since 2020 were evolved a lot, and the people that maintain source verify, they no longer maintain. So there is a lot of like it's not probably like now the recent version of the Solidity compiler will not work with. And yeah, it's really nice because like it's a source verify use what verification community done like many years, the boogie verify as a backend. So it's really like using powerful backend tools. And only what it does is just translate Solidity to that boogie. And there like you use all the what verification community done for the last 20 years. So you only need to maybe like if somebody took a charge and just like update it to the recent Solidity compiler version, you get all the bonuses from what verification community done for the last 20 years. Because like source verify is just like you can think of it as a a nice parser that pass solidity to prove it.
All right, any other questions?
We have time.
Okay, well, let's thank our speaker again.
Thank you very much.